I was talking about this paper by Drake and Campins, and when they talk about cometary water, they mean that they use this term in the sense that I described before. That is a late veneer of comets impacting the Earth long after it was formed. Now, then against this, they mention an observation by Alan Stern and others who found the solar argon to oxygen ratio in Comet Hale-Bopp. But if you look at that detection, it's very weak, I would say. You really cannot trust it. And others like Hal Weaver and other collaborators have found much lower argon ratio in two other comets. Now, the argument here against comets would be that if comets had a solar ratio of argon to oxygen, then, and if the oxygen was brought to Earth mainly by comets, then the Earth should have had much more argon than we have. But as I said, I don't think we can trust that observation at all. But the other thing here is more interesting perhaps. It relates to an isotopic ratio of osmium of the Earth's primitive upper mantle, which agrees with anhydrous but not carbonaceous chondrites. So let me tell you what that means. This is not so evident. But here you have sort of explanation. The primitive upper mantle of the Earth turns out to have an abundance pattern of highly siderophile elements, which is like that which we find in chondrites. Highly siderophile elements, it's those elements that have sunk to the Earth's metallic core with iron when the Earth differentiated. Now, if the small quantities that you do find of those highly siderophile elements in the Earth's crust, the Earth's primitive upper mantle, don't ask me how you measure that and how you define it, but it's some quantities of those elements that you find there. And if that had been just the remainder, what was left after most of these elements differentiated down into the Earth's core, then you would not expect a chondritic abundance pattern. So this rather indicates to those geochemists that those siderophile elements came to the Earth after differentiation by meteoritic bombardment, chondritic bombardment. So that is a sort of late veneer of material to the Earth by meteoritic bombardment. And then you can use this osmium isotope ratio, because one of these osmium isotopes is a daughter product of rhenium, which is another highly siderophile element. And the initial abundances of rhenium versus osmium will determine then which ratio you have. And that is different in different meteorites. And this histogram shows you clearly the difference between carbonaceous chondrites here, enstatite chondrites here, and ordinary chondrites here. And the Earth's primitive upper mantle agrees fairly well with ordinary chondrites, but not with carbonaceous chondrites. And now the argument of Drake and Campins is that this appears to show that the late veneer that came to the Earth was not carbonaceous chondrites. It was rather like ordinary chondrites from the inner asteroid belt. And I couldn't agree more. I think that the late veneer that came to the Earth actually came from the inner part of the asteroid belt and did not bring much water at all. So in that sense, I agree with them. But we will see that the water could still have come from further out. Let me now tell you a bit about this cometary late veneer, the standard picture of a cometary late veneer. That used to be the standard explanation for the Earth's water, say about 10 years ago. Most people believed that this was where the water came from. But this was first challenged by the discovery of this apparent discrepancy between the D to H ratios in some comets and the Earth's oceans. So that was the first shot against this idea. But later on, there have been more important criticisms against this idea. Now, if we look into the idea of this late veneer, this cometary late veneer, it goes like this. The classical recipe for giant planet formation was that the cores of the giant planets formed in situ, where the planets are now observed. So Jupiter's core formed at 5 AU, Saturn's core formed at 10 AU, Uranus's core formed at 20 AU, and Neptune's core formed at 30 AU. And to form these cores, you need some time. And this time scale increases strongly as you go outward. So for Jupiter's accretion, you would expect that this could be done perhaps in the time scale of 1 million years. Whereas for Neptune, you would need 100 million years to form the core. Now this at once shows you a problem. How could you explain the presence of solar nebula gases, hydrogen and helium in Neptune? Because this must have been captured from the solar nebula, which only existed for some billions of years, say 5 million years or maximum 10. But so that's a problem at once that one can identify. But this, anyway, is the classical recipe that people had in mind. So then, if you continue along this idea, it shows you that simultaneous with the accretion of these planetary cores, there must have been also gravitational scattering into Earth-crossing orbits by failed planetesimals, if you like. And that should have occurred on the same timescales. And looking at this 100 million year timescale for the growth of Neptune, also for Uranus, practically the same, that would have meant then a long-lasting bombardment with a decay time constant of the order of 10 to the 8 years from these Uranus-Neptune's accretion zones. So you would have had an infeed of material from those zones that went on long after the moon-forming impact. So that could have explained the late veneer to the Earth. And then you look at the lunar cratering rate. The diagram here shows the cumulative crater density on the lunar surface as a function of the age of the surface. So different surface elements on the moon have been dated from the Apollo samples. And if you count craters on different parts of the moon where the surface is made up of material that you have dated from somewhere, then you can plot the crater densities versus the ages. And this is a linear scale, and on the y-axis you have a log scale. So the curve looks strange, but this part of the curve shows you constant cratering rate. Back to 3.5 billion years ago or something like that, and before that time the cratering rate was much higher, and it fell rapidly with time. from 4 billion years about until 3.5, there was a strong decrease of the cratering rate on the Moon. Now, we cannot say really directly from these measurements whether this decrease was just the final stages of a decrease that went on all the time from the formation of the Moon, or whether it was just a temporary peak that happened around 4 billion years ago and then faded away.
Do we know how they have dated these impacts?
This is usual radioactive dating, like rubidium, strontium, or things.
Yeah. So it means that they really visited that many places.
Yes. Well, interesting. But they have something like 6 Apollo landings, I think.
So the budget.
Okay. Yes, well, it's not easy to say really, so people have had different ideas about this. But Chris Chaba is one of those who thought that this is likely to be just the end of an exponential decay with a time constant of the order of 10 to the 8 years, which went on until the end of this heavy bombardment period. And if you use that assumption, then you can take this extrapolated curve there and integrate the amount of cratering, the amount of impacts, and find the time-integrated impactor mass. And on the Moon then first, and then you scale it to the Earth. And for the Earth you find that from 4.4 to 3.9 giga-years ago, the Earth would have accreted of the order of 2 times 10 to the 22 kilograms. And that's several times the amount of water that we have in the Earth. So if this impacting material was cometary, that is largely water in composition, then you would have brought to the Earth more water than you need. And so, okay, this appeared to be a good explanation for the origin of the Earth's water.
Just a technical question.
Yeah.
The earliest points then, are they determined, let me put it this way, could one be able to date earlier times? Because you said you had to extrapolate this curve, why don't you measure it directly? Or is there a cutoff in radioactivity so that you cannot date earlier than 4.5 billion years, that's it?
No, there is no such cutoff. But
Okay.
You could imagine that everything was shocked during this period of extremely heavy bombardment, so that all the radioactive clocks were reset all the time until this period when,
Okay.
it's possible to think like that. But there are some problems with this picture, and I think that most of the researchers nowadays do not believe in this picture of an exponential decay that we just see the tail end of. So this picture has been increasingly challenged in favor of an episodic late heavy bombardment. So that's one thing. Another problem that I will describe is that of explaining the amount of impacting cometary material on dynamic grounds. That's also a serious problem. How could we explain how so much material could have come from Uranus and Neptune and bombarded the Earth? And the third important issue here is that new models of planetary formation, giant planetary formation, involve something new, that is radial migration of the planets due to scattering of the planetesimal disk if not due to interactions with the gas disk. But just due to scattering of the planetesimal disks, the planets or protoplanets should have migrated considerably in the radial sense. And I will show you some examples that completely overturn the picture of how the giant planets were formed and where they were formed. So about this late cataclysmic cratering episode, I summarized some of the arguments here, why many people tend to believe in this cataclysmic episode. One is that there is no trace of this 600 million years continual lunar cratering before 3.9 gigayears ago, in the sense that there are no impact melt rocks older than about 3.9 gigayears in the Apollo lunar samples, nor in the lunar meteorites, which come from a little everywhere on the moon. So no rocks formed by solidification of impact melts earlier than 3.9 gigayears have been found, which would be a little surprising if we would have had this strong bombardment going on over time. There is also no crustal enrichment in siderophytes, and this is the argument that I told you about the osmium isotopes. If after the moon formed from essentially terrestrial mantle material, which was very poor in those extremely siderophile elements, if there would have been bombardment of the lunar surface bringing in a lot of those highly siderophile elements, one would have seen such an enrichment in those elements. But there is no evidence for that. There is also no trace of large impact basins, like the large Maria basins that we see on the moon or the South Pole Aitken Basin. There is no trace of large impact basins before about 4 gigayears ago, which again would seem a little surprising if we would have had bombardment and creation of many large impact basins before that time. One should have seen some trace of it. And the final item here is the early oceans on Earth, which again speak against an extremely high impact rate at those early epochs. So the current idea seems to be more, many different people may have different ideas, but many think that we, to begin with, we had a comparatively quiescent period on the Earth and Moon. And then we had this cataclysmic cratering episode around 3.9 gigayears ago. And if we just take the total mass of late heavy bombardment Earth impactors during this episodic period, then that amount yields less than 10% of the Earth's water. So it appears then that this late heavy bombardment could not have delivered the Earth's water. Just a small part of it. About the dynamical constraints, here is a summary. It's easy to estimate what is the chance for an Earth-crossing object of hitting the Earth per orbital revolution. If you just take an Earth-crossing object, it has an orbit that enters within a sphere of 1 AU around the Sun and then comes out again. Each orbit, it crosses the sphere twice. And you can calculate the cross-sectional area of the Earth for colliding with the Earth. Some gravitational focusing, you include that, and then you find an area which you can compare with the total area of the sphere. And then you can just easily estimate the random probability of collision per orbit. and you will then find something of the order of 10 to the minus 8. More or less, 10 to the minus 9 to 10 to the minus 8. And if you use that, then for asteroids from the main belt, we have near-Earth asteroids and Earth-crossing asteroids that come from resonances in the inner part of the asteroid main belt. They spend of the order of 1 million orbits in Earth-crossing orbits before they finally collide with the Sun, typically, or are scattered away. So if you take that and multiply by 10 to the minus 8, you will find a total impact chance per object of 10 to the minus 2. So 1% of them might be expected to impact the Earth. For comets, they have orbits which are more unstable because their orbits also cross the orbit of Jupiter, and Jupiter will scatter them away on a short time scale. So the lifetimes here are just 10 to the third, 10 to the fourth orbits. So multiplying by that again, we get a total impact chance of 10 to the minus 5 to 10 to the minus 4 per object of colliding with the Earth. That is a bit uncertain still because it depends on the probability of decoupling from Jupiter, which is not very well known. But I think that we have to estimate it like that, 10 to the minus 5 to 10 to the minus 4. So when you have these impact probabilities, then you can easily estimate that to acquire 10 to the minus 3 Earth masses of water from comets, even if they were 100% water, you would need of the order of 10 to 100 Earth masses of potential impactors, that is, Earth-crossing objects coming from those source regions near Uranus and Neptune, which is a lot of material. Probably we can say that it's too much if coming from Uranus and Neptune. And it might be too much also if it came from Jupiter, Saturn. So that's I think, a strong argument against this late veneer of cometary water coming from Uranus and Neptune. One can also say that to acquire the same from asteroids with about 10% water, like the carbonaceous chondrites, you might only need about 1 Earth mass of potential impactors, which seems much more reasonable. Now, I would like to show you a little of this planetary migration models, how they can change the picture. And this is these are results that were published in 2005 by a group led by Alessandro Morbidelli from Nice Observatory. So it's called the Nice model, involving Rodney Gomez and other people as well. They assumed that the system of giant planets started out as a very condensed system, where you had Jupiter here, Saturn here. Jupiter is about 5.5, Saturn at 8. This is Neptune at 11.5, and this is Uranus at 14 KU. Well, we don't know which one is Neptune and Uranus really, but it appears that in this simulation it was like that. First, you consider the scattering away of remaining planetesimals from this zone during the time that the solar nebula existed. They did this in a very simplified way, but they found that the lifetimes of those planetesimals were quite short, say less than 10 to the 6 years, in the whole of this area, of this zone. So it's shorter than the lifetime of the gas disk. Therefore, the scattering away of those planetesimals would not change the orbits of those giant planets very much, because the gas disk is clearly the dominant feature here, and the planetesimals is only a small fraction of the mass. So they don't consider any migration to occur during this time that the gas disk existed. But by the time that the gas disk was blown away, here, you had still a lot of planetesimals around, say, starting from 1 AU outside the orbit of the most distant giant planet. So there you have a planetesimal disk that continued out to 30 AU. And what then happened was that this planetesimal disk started to be slowly eaten away by these giant planets, in the sense that resonances started increasing the eccentricities slowly by some planetesimals in this outer disk, so that the eccentricities increased and their perihelia came into crossing conditions with respect to the outermost giant planet. And then you could have close encounters, and they were scattered away. They were handed in by this planet to that planet, to that planet, to that planet, and then scattered away. So there was a sort of juggling of planetesimals between these giant planets. And as a result, they started to migrate, slowly but surely. With the result that the separation between Jupiter and Saturn increased with time. Jupiter migrated inward, Saturn migrated outward. And at some time, these two planets came into the 5:2 mean motion resonance. And that appears from their simulations to possibly have occurred at the time of the late heavy bombardment. It could have occurred at practically any time, but say that the time of the late heavy bombardment is one of the options. At that time, you could have had this resonance crossing. And then, this whole system of giant planets just went havoc. Very rapid chaos was created, and you had close encounters between the giant planets, so that Uranus and Neptune were thrown out by encounters with Saturn, and then they were circularized by dynamical friction from this planetesimal disk, and they ended up more or less in their current orbits. The diagram on top here shows the evolution of these orbits, perihelion and aphelion distances. Jupiter finally is here, Saturn a little higher up, and then Uranus and Neptune. And you can see that Neptune started out inside Uranus in this simulation. Now, as a result of this evolution, first of all, when Uranus and Neptune started moving out and quickly emptied this zone of planetesimals, more or less, many planetesimals would have been brought in to Earth-crossing orbits and collided with the Earth. So that would have been a cometary bombardment, which, according to this picture, well, evolved with time like that, and then quickly increased as these planetary orbits started going outward. But then you would also have had an asteroidal bombardment, because when this new system of giant planets was set up, during this time, the resonances, mean motion resonances in the asteroidal belt, and also the secular resonances, swept through the main belt quickly. And therefore, the eccentricities of the asteroids were increased, typically, so that a large fraction of the asteroids that were still around at that time were lost. They came into Earth-crossing orbits, bombarded the Earth, or they came into Jupiter-crossing orbits and were sent away, or they collided with the Sun. So the asteroid belt was emptied, practically, during that time. And what you have now in the asteroid belt is just a small fraction that was able to survive. So we would have had an asteroidal bombardment as well as a cometary bombardment. And they are not able to say really which bombardment was predominant. But they argue, Morbidelli argues, that the late heavy bombardment created size distribution on the Moon agrees with the size distribution of asteroids in the main belt. and therefore he thinks that the asteroids were likely dominant. Now, if that is the case, I would say that the late heavy bombardment on both the moon and the Earth mainly came from the inner part of the asteroid belt, which means that these siderophile elements that came to the Earth would have had a ratio of rhenium to osmium, which agrees with ordinary chondrites rather than carbonaceous chondrites. And no problem, that's what we see. And we didn't get much water. So where did the water come from? Well, I think that an idea that still needs to be explored is that of an early exogenous source of water. Let's come back to this diagram from the Nice model, this diagram. The scattering away of all these planetesimals, icy planetesimals, from the giant planet zone, when the gas disk existed. This should have led to some objects coming into Earth-crossing orbits. So the clearing of this region should have occurred quickly, on a timescale less than a couple of million years, could have brought a lot of icy material inside the snow line. If the snow line was situated somewhere near 5 AU or so, now where was the snow line? Some people like Dave Jewett, after discovering these Themis family asteroids with a lot of ice in them, argue that perhaps the snow line went inside 3 AU at some times. Well, why not? In principle, one could think that at least temporarily one was able to condense ice in that region of the asteroid belt. And I don't think anybody knows really. But to me, it seems a little remarkable if the snow line really was so far in that no big planet was formed inside the orbit of Jupiter. Because it appears that that's where we have the icy objects like Jupiter's moons. And if we had formed a lot of icy material at closer distances, why didn't the planet form closer in? So, well, it's just ideas like that that make me think that the snow line was rather somewhere near 4.5 to 5 AU than 2.5 AU. Now, if the snow line was really as far out as that, then the ice that we see in the Themis family should have been brought in from outside. And maybe from this clearing of the region of the giant planets. So we could imagine the delivery mechanism here as follows. The growth of Earth mass and larger planetary embryos in this Jupiter-Saturn zone in particular should have led to the scattering of a huge number of icy planetesimals, IPs, at a time when the gas disk, the solar nebula, still existed. Okay, that's clear. So this scattering should have led to some IPs being brought into small perihelion distances, that is, orbits approaching the Sun, much closer than the region where they came from. So they went into elliptic orbits with smaller perihelion distances, and then got their orbits circularized by gas travel, and thus ended up in the outer asteroid belt. Okay, this is just an idea. It needs to be tested. And then, if we got ice into the outer asteroid belt, okay, that's part of the route we need to follow. But the remaining part is then that parts of the terrestrial planets may have been brought in from that region in the form of carbonaceous chondrite meteorites. And there is some recent work that I will show you in a minute that indicates that that could have been the case. First, to show you the dynamical transfer routes that we have in mind. Here, you imagine a protoplanet. In this case, I put it just at Jupiter's distance from the Sun. And this diagram shows aphelion distances versus perihelion distances. And gravitational scatterings by close encounters with this protoplanet or planet moving in a circular orbit there will change the orbits along the blue curves that you see here. Curves of constant values of the Tisserand parameter. So the planetesimals might be pumped up in eccentricity here, hit the curves somewhere here, and then being brought down like that. This gravitational scattering is bidirectional. They could go in both senses and finally be ejected from the solar system. Or they could come first inside. And then you have this gas drag according to the green curves, which will tend to decouple them from this gravitational scatterer. And then if the scattering went down to this sort of region here and then the circularization occurred, then you might explain that you got a lot of ice into the outer asteroid belt, but perhaps not the inner part. So we have a project now in Uppsala where we want to do simulations of this process. Gravitational scattering, not by one protoplanet, but by a set of planetary embryos that grew in that region, in the presence of the gas disk. So combining scattering by gravitational kicks at close encounters with these planetary embryos, and then the gravity of the disk and the gas drag effect on the disk should also be included. And we want to simulate that and see where the eyepiece end up. If we can explain that we somehow watered the outer part of the asteroid belt, but not the inner part, that would bring us a long way toward explaining the Earth's water, probably. So we will see what happens, but this is at least an idea. And the rest of the explanation comes here. The growth of terrestrial planets. This has been done already by John Chambers and George Wetherill and others as well, Jean-Marc Petit. These are simulations where a lot of planetary embryos and planetesimals were started all over the inner solar system. The semi-major axis here goes from 1/2 to 5 AU in each of these four diagrams. And you see four different snapshots of the evolution. So to begin with, you don't have Jupiter. You enter Jupiter suddenly after 10 million years. And as Jupiter arises, the main belt embryos are caught in resonances, their eccentricities are increased, and some of these embryos are accreted by the embryos in the terrestrial planet region. And the main belt is efficiently depleted. And this is something which should have occurred very early on, as you can see. So already during this time, the initial asteroid belt should have been strongly depleted. And then came this extra depletion at the late heavy bombardment, perhaps. But, okay. What one seems to get from this picture is that, first of all, you might explain the existence of a couple of terrestrial planets in this zone, and very little material remaining further out. Second, that some part of these planets that are created here came initially from the outer part of the asteroid belt. So that could have been icy material that came into the terrestrial planets by these giant impacts. And Morbidelli et al. Wrote a paper already in 2000, based on those simulations, where they argued that, okay, in general, the Earth should contain something like 1 or 2 embryos from the region at more than 2.5 AU from the Sun. And if those embryos are as hydrous as the carbonaceous chondrite meteorites, then there is more than enough water for the Earth's planet. The caveats here are that these are small number statistics. Of course, 1 to 2 embryos. It means that you might expect perhaps different amounts of water in different planets, depending on how many embryos they accreted. Maybe one planet accreted 0 and got no water, and another planet accreted 5 and got a lot of water. But who knows? But there is a possibility to have a variation, a clear variation of the content of water between the different planets. But, okay. Another issue is that of loss of water during the accretion of these embryos, because these are giant impacts. These are like the moon-forming impact, very energetic events, where you need somehow to explain how the water of these icy embryos was retained in the Earth as it accreted them. So, and then extra loss of water during the final giant impacts, like the moon-forming event, also needs to be treated somehow. Nobody has explained actually what happens to the water during the moon-forming impact. So this needs to be done as well. But so let me summarize. What we have seen is that the endogenous water, even if one can imagine that the grains of the nebula were able to absorb some water molecules, it seems that the dryness of the asteroids in the inner part of the main belt argues against the absorption of a lot of water onto the grains in the Earth's region. So that seems not to be a very, very attractive idea. And the late cometary veneer, as I told you, is practically out of the question. Dynamical difficulties in explaining the amount of water, and also evidences against this continual heavy bombardment speaks against that. And also other evidence, like the osmium evidence, that seems to show that the late veneer was not cometary, but rather asteroidal. Okay, then we are left with this early exogenous source that could have come from the formation of the giant planets, the scattering of icy planetesimals from there. Or possibly, if the snow line came into the asteroid belt from time to time, then condensation of ice there could also be a possibility. But a rich exogenous source probably existed, at least while the giant planets formed, and it remains to be seen how much water could then have been brought to Earth from this region outside the snow line. And that's practically where I wanted to finish. So the final question then, if we are led to believe in an early origin of the Earth's volatiles, it of course makes them vulnerable to the accretion of giant impacts, including the moon-forming event. On the other hand, the lack of a relevant late veneer to replace the lost water means that these impacts somehow must not have desiccated the Earth. So this again is the problem. Can this be understood? I think likely it has to be understood. But how? So, René, you can be happy. I finished in time.
Great, thank you.
So, now we can take questions.
About, well, on the
Active field.
the snow line in the very early this there was an effective heating of the sunlight, meaning that it would be much cooler than one would believe when it's starting to dig in. It could be maybe further chaos position of the Earth, just like that. But I mean, when the material around this is not that cooler. Because the problem here, the raised over time was when the moon formed, it seemed that it was formed by catastrophe, but is that really true? That it formed as a double planet?
That the origin of the moon is a giant impact and not something else. Yeah. There are a lot of arguments around that issue. If the moon formed together with the Earth as a binary object, forming at the same place with us, then I think the argument is that the composition is so different. The moon actually appears like a sample of mantle rocks from the Earth, but desiccated. So it's difficult to see how formation as two separate objects at the same place could have led to such different compositions. I think that's the main argument against that picture.
So there is too little iron, for instance.
Yes. There is some iron, probably a metallic core in the moon, but it's very small.
With this,
Yeah.
I might have understood the question also, with this migration of planets, could it have been that the Earth captured the moon at some point?
Yeah, that's another popular idea since a long time, that the moon could have been captured. And it's not impossible, although it's very difficult. But again, the moon has a very strange composition for an object that somehow was formed from chondritic material. So again, it's not a popular idea anymore because the moon is so poor in metals. So how could it have been formed anywhere with that kind of composition? So that's the main reason to think in terms of the giant impact, because then you get it from the Earth's mantle rather easily.
What is known about the other moons of other planets?
The Galilean moons of Jupiter, for instance, there you have Ganymede and Callisto, which appear to be like 50-50 rocks and ice. And that's more or less what you would expect from condensation of material, including ices and crystals. So nothing particular there. Io has lost all the volatiles due to tidal heating from Europa, also has lost theirs. So you can explain those things. And Saturn's moons again look like they could be, well, they are perhaps a bit too icy, but that could correspond to the local conditions in the planetary nebula. So, well, it appears to be consistent with the condensation at those places.
So it means that those planets were formed next to or outside,
Yes, all these planets must have formed outside the snow line, for sure.
yeah.
And according to these simulations that I showed you, perhaps Jupiter formed at 5.5 something.
In regard to what you said last, I was a little bit astonished. How is this Nice model treating migration? Because you said,
Yeah.
Jupiter was moving inwards, and this is a standard picture
Yeah.
of migration. But you also said that Saturn was migrating outwards.
Yeah,
this is not really standard.
No. Remember, this is scattering. This is migration due to planetesimal scattering. It doesn't have anything to do with interactions with the gas disk. So the interactions with the gas disk have been completely neglected in this
Oh.
problem.
But
Of
the
course,
gas drag
we
is
could have had
probably
a-
more important when it
Well,
comes to exchange of angular momentum,
yes,
I guess.
Yes, but how much do we know about
No,
that? But no, they just neglected that and looked at what happened due to the scattering of planetesimals.
Mhm.
And then the typical result is that the innermost planet moves inwards, the others move outwards.
Mhm.
I don't think that the Nice model is the last word at all, but it appears rather attractive because it explains a number of things in the solar system, like the existence of the Trojan asteroid populations, the existence of irregular satellites around the giant planets. So,
And then there was a final question from my side. You have been mentioning two components of dust or planetesimals or whatever you call it,
Mhm.
asteroids and the Oort cloud, right? What about the Kuiper belt? What kind of source of volatiles could that be? Is there anything known from observation?
yes, we know that the classical Kuiper belt and the scattered disk seem to be comparable in mass and number of objects. And we also know that the scattered disk is interacting directly with Neptune, while the classical Kuiper belt needs to be pumped up in eccentricity first by resonances. So the scattered disk is a much more efficient source for bringing material in toward the Earth than the classical Kuiper belt. And since the two populations are equally massive, we believe that most of the Jupiter-friendly comets that we have today come from the scattered disk, not from the classical Kuiper belt.
Mm-hmm.
That's what is believed, at least. Of course, the classical Kuiper belt is also a source of material, but a less efficient one. And also, another feature of the Kuiper belt is that it has two components, not just the classical Kuiper belt, which is a cold population with rather small inclinations, but there is also a hot component with much more inclined orbits.
Mm.
That is very difficult to understand by classical scenarios. While due to this migration picture of the Nice model, you can explain the emplacement of this hot population from due to the migration of Uranus and Neptune.
Mm-hmm.
So it's possible that those two components of the classical Kuiper belt came from somewhat different places as well. Yeah.
Other more questions? Yeah.
I have a question of, is nowadays the form of the Earth. If I check our form without water, the form of the Earth is not really spherical form. It's just like, very, I don't know how to describe the form of the Earth without water. So if we had water, so we look at the spherical form compared with all the dry planets. I wonder, are there any relations between the shape of the Earth and the way how the Earth keeps the water for a long time? Because you said that the source of the water on from the outer, from the state, from the. So I wonder the relation, have any relation, or you have any idea about that?
I'm not sure if I understood.
Yeah, yeah, I'm sorry about it. But the point, I guess without water, the form of the earth in a spherical form.
Uh-huh.
Yes. So.
I don't know.
I just because I read from the science paper. They had the view of the 3D dimension of the earth without water. It's not the spherical form. So I wonder how have any relation between.
Yeah, I'm sorry, I cannot comment on that. I haven't read that literature.
Yeah.
So. Okay.
Okay, let's thank once again.